All right, so let's take a look at how we can use an op amp to perform a sum on a couple of input signals. So I'm going to draw my circuit like this. I'm going to ground my plus input. I'm going to draw my feedback resistor here, right there. And then I'm going to draw two different resistors coming together into my minus terminal input. And I'll call this V1 and this V2 some voltage inputs. I'll call this R1 and I'll call this R2. And then obviously this is my RF and this is my V out, okay? So right off the bat, we know that since this is 0 volts here, we know that this is also 0 volts. And then I'm gonna have, I can perform KCL at this node to go ahead and solve my circuit like I've been doing. I'm gonna call this current I1, I'll call this current I2, and then the current that comes out of this node right here is this current, which is the same as this current, right? Because no current flows into the terminal of my op amp. So I'll call this IF, which is equal to this. And let's go ahead and write some expressions for those currents. IF is going to be, well, it's going to be the drop across my resistor going this way divided by RF, which is 0 volts minus V out divided by RF. And then for I1, it's going to be the drop across my resistor going this way, which is going to be V1 minus 0 volts divided by R1. And then for I2, it's going to be V2 minus 0 volts divided by R2. Okay, so now I can, KCL at this node tells me the sum of the currents entering is equal to the currents leaving. And so I can go ahead and write that out. V1 over R1 plus V2 over R2 is equal to negative V out over RF, right? I can multiply both sides by RF, so I get RF over R1 times V1 plus RF over R2 times V2 equals negative V out. And then I can multiply both sides by -1. Let me get back to black here. And I get that minus RF over R1 times V1. Oh, sorry. Minus RF over R1 times V1 plus RF over R2 times V2 gives me V out, okay? So I have an expression for V out. It's not very satisfying. Definitely doesn't look like what you might expect from a summing circuit. But what would happen if I let RF equal R1 equal R2? And so basically what I'm saying is all three of my resistors are the same size. What would happen? Well, if I come back down and look at this equation, if RF and R1 are equal, then this goes to 1. And if RF and R2 are equal, then this goes to 1. And then what I'm left with is V out is equal to negative V1 plus V2. And so that's a lot more satisfying, right? That's my output equation. Or actually, let me make it a little bit bigger. That's my output equation, which tells me that my output is just the negative of the sum of the two input voltages, right? So that's pretty nice. But maybe that still doesn't satisfy you. Maybe you don't like that that's negative. So there's something I could add to this circuit in order to flip that, which we've already learned. Well, I can add an inverting amplifier. So what if I add an inverting amplifier like such? That just has a gain of 1. And so if I wanted to have a gain of -1, let's go back to our inverting amplifier slide. My inverting amplifier tells me that if I want to get a gain of 1, I can use this equation here. I guess I haven't really explained what gain is. I keep using the term. Gain is the V out over V in. So if I were to rearrange this to get V out over V in, I would get minus RF over R1. In this case, this is my RF and this is my R1. But I don't want to use the same, let's just call this RF2 and we'll call this R3 so that we don't get confused here. So if I were going to substitute those into this expression, it would look like this. Okay, and so what I'm saying is that my gain here, my V out over V in, basically the ratio of my output to my input signal, is equal to negative RF2 over R3. If I want to get a gain of -1 so that I can take this, basically this output signal, which is right here, that's my V out that I'm going to pass as my input into my next stage here. If I want to get that to be positive, then I need to multiply it by a gain of -1. So if I want this to be -1, that just means RF2 and R3 need to be the same size. So if I let those be the same size, then I get V out over V in is equal to -1, or V out is equal to -1 times V in. And in this case, my V in is my previous output. So my final V out here, I'll call it V out final. V out final would be equal to -1 times V in, which in this case is -1 times V out from the first circuit, which is -1 times this piece here, which is negative V1 plus V2. My negatives would cancel, and I would be left with V out final is equal to V1 plus V2. And so if I want to use my summer to get a positive sum of the two input voltages, I can do that by meeting a couple of conditions. By first making sure that for my summing stage, or this first circuit here, I wanted to use the laser pointer, I have to ensure that RF is equal to R1 is equal to R2. And if I want to do the second stage and get my negative sign, which is down here, to go away, then I need to implement an inverting amplifier, which will give me a gain of -1, so that I can take my output from my first stage and feed it into an amplifier with a gain of -1. And what I end up with is my final output voltage gives me the sum of my initial two input voltages. Okay, so that's quite a bit to swallow, but let's just go ahead and end this video here. This kind of shows you the first example of cascading multiple op-amp stages, or multiple stages in a circuit at all, where you can take the output of one circuit and pass it in as the input to another circuit. This is a very common practice in signal conditioning, reading sensor outputs, etc. And so in the next video, I'm going to go ahead and just solve an example problem where we solve for the output voltage given a similar configuration, and we go ahead and use what we just learned from this summing configuration, really just using the op-amp golden rules and KCL like we've been using, but just to perform a different function. Okay, so let's go ahead and end this video right here.